Okay, Chapter 8, Section 1, Arc Length. Okay, in this section, we're going to figure out a way to determine the length of a curvature. So let's say that we have this curvature right here, and we want to figure out the length for it. Well, we're going to start off with an approximation. And the first approximation is probably not going to be very good, but we're going to build on a pattern that we're going to establish. So for my very first approximation for the whole length of this curvature is going to be to convert it into something that we can easily calculate, the length of a straight line. So let's say that we put some notation on here. Let's call this point, starting there, we'll call that point naught, and we'll call this point over here point 1. Right, so I want to get the curvature of the blue line from point naught all the way out to point 1. So my first guess is going to be to draw a line that starts from here and extends out to there. So there, the length of that red line could be my first approximation. Now, notation-wise, let's use the notation P naught P1 like this to mean the length of that red line. Length of line segment connecting point P naught and P1. Okay, so there's my first guess. Obviously, not a very good guess, right? So let's move on past this and move on to an even better guess. Okay, so now what I want to do is, again, label this as my P naught, except I'm going to break this up into 2 points. So somewhere halfway through this process here, about right in the middle there, I'll go around there and call that P1. And then we'll come out over here and we'll call this P sub 2. Okay, so now I'm going to create 2 line segments. One of them is going to start off there and extend out to there. And the other one is going to go from there and extend out to there. So already we could see that this is a much better approximation, right? So now we can say that the length of that curvature, the blue curvature, I'm going to guess that it's going to be approximately equal to the sum of the length of these 2 segments. So it'll be P naught P1, right? That's the length of this first segment connecting point P naught and point P1, plus the length from P sub 1 out to P sub 2. Okay, so that's a better guess, but we could do better. And you could see the pattern that we're establishing here, right? So let's go over here and do one more. This time, let's break it up into 4 different points, giving us 3 different segments. So let's call this P sub 0, and then somewhere around here, we'll say this is P sub 1, and somewhere over here, we'll say that's P sub 2, and finally over here, we'll say that that's P sub 3. Good. So now when I want to approximate it, then I can insert these line segments. One of them will connect from this point to that point. Another one will connect from this point to that point. Another one will connect from that point to that point. Okay, so as you can see, the sum of these these three line segments would make an even better approximation. So now we say that the curvature, the blue curvature, is approximately going to be equal to the sum of the segment between P0 and P1 plus the segment between P1 and P2 plus the segment between P2 and P3. Okay, so that's a much better approximation, but now let's get really serious with our approximation. Let's say we really want to get a pretty good approximation, so we're going to start breaking this up into lots of pieces. Let's call that P0 there, let's call that P sub 1 there, let's call that P sub 2 there, and so on and so forth, so on and so forth. And we keep going, all the way around, until we do this n different times. So that last one we're going to call P sub n. Okay, and so now we're going to have a bunch of little line segments here. So we'll have a line segment from there to there. And a line segment from there to there. And a line segment from there to there. And a line segment from there to there, and so on and so forth, so on and so forth, until we get to over here. We have a line segment from there to there. Right, so all these red ones so we'd have a line segment from there. So we'd have a line segment from there to there, and then another one from there. Oops. Another one from there to there, and another one from there to there, and another one from there to there, and so on and so forth. Right, so somewhere over here in the middle, we'd have one from there to there, and another one from there to there, and another one from there to there, right? So I'm just skipping a few here. And then eventually we'd come down here and get that last one, that nth one over there. Okay, so we have all these little straight lines all the way around. And so now we can do a much better approximation. We'd say that that curvature L is equal to, well, it would be, okay, so then we'd say that the approximation of the blue curvature would be equal to this following sum. It would be P0 to P1, right? And this notation means it's the length of that line segment connecting P0 to P1, plus the length of the line segment connecting P1 to P2, plus, and then a bunch of stuff there. Let's skip that for now. And then the very last one is going to come over here. So it'll be at the end here, plus the line segment connecting, and this should be Pn minus 1, and then P sub n, right? Now in the middle, let's think about that pattern that keeps going. Somewhere in the middle here, there is an ith one, so P sub I, and then the one that came right before it would be P sub I minus 1. So then that line segment would be somewhere in the middle of this summation. It would be the length of the line segment connecting P sub I minus 1, P sub I, plus, and then we continue with that pattern that way, and we can plus continue with the pattern this way. Okay, so then we can replace this whole thing here by saying it's a Riemann sum. Riemann sum as I goes from 0 to n of P sub let's see, what do we want? Let's make sure that the numbers match here. I want my first one to be, I want my last one to be I, and it stops there, I, and then let's make this one I minus 1. But then if I start at 0, I end up with minus 1 there. So I don't want to start at 0, let's start at 1. Okay, and so that makes that first one, if we replace the I with a 1, we get 1 minus 1, that's P sub 0, and 1, that gives me that first one. And then if I get to the very end there, then I stop at n, so it'd be n minus 1 and n. Okay, so that whole summation right there is equal to this, and that becomes a pretty good approximation of the curvature of n. Okay, so let me zoom out and let's take a look at the progress we made here. Okay, so remember, we want to get a pretty good approximation of the length of this blue curvature. We start off with one single line segment like this, right? So that's my first guess, a pretty bad guess. Then we go, okay, well, let's do 2. So then that's a better guess. And then we can do 3. That's an even better guess. And then we're like, okay, let's stop messing around. Let's do it for n of them. So we can do n summations, n segments here. And then we add them all up. And then that makes a much better approximation of the blue curvature. Okay, so that's the general idea of where we're heading in this section. But before we move forward, let's spend a little time thinking about the distance formula for line segment. So we're going to need that in this section. And then we'll do a more formal presentation of exactly how we want to break up the domain and the notation we want to use to write down a sum. And then, as you might have guessed, to really get a really good guess, we want to set it up like this so that we have an equation involving n segments. And then we want to apply the limit as n goes to infinity to that and hopefully be able to solve it so that we can get an infinitely good approximation of the length of our curvature. Okay, so now let's just pause for a second and let's go back and think about the distance between 2 points, the length of a segment connecting 2 points in space, the distance formula. Okay, so let's take this first approximation and work with it a little bit. So we want to find the length of the red line as an approximation to the blue, of course, but just for finding the purposes of finding the length of the blue line, we don't really need, for the purposes of finding the length of the red line, we don't need the blue line. So let me erase that. Okay, so presuming that this red line is some line segment in a Cartesian coordinate system, let's say that it goes like this. Here's my x-axis, here's my y-axis. Okay, well, presumably this would be the input value, some x sub naught value perhaps, and over here we'd have some x sub 1 value there. And then there would be some output value associated with the x naught. So perhaps this right here is y sub naught. So the x naught presumably would lead to some y naught value. And then the x sub 1 value would presumably lead to some y sub 1 value. Good. So then this p naught value is also, could be written this way, or it could also be written as p naught, which is also a x sub naught comma y sub naught. And this one written as x sub 1 comma y sub 1. Good. Okay, so we want to find that distance, that red line distance. So what we want to do is think about the triangle that is formed underneath it in the following way. Let's use the color blue, I guess. Let's use blue. And let's insert a line that connects this all the way out to there. And another line that connects this down to that. Okay, so now we've formed a right triangle where the red line is the hypotenuse of our triangle, so we know that Pythagorean theorem tells us that this side squared plus this side squared must be equal to that side squared. Good. So this side, this whole length right here, this is equal to x sub 1 minus x sub naught. Good. And this side here is equal to y sub 1 minus y sub 0. Good. And this, well, that's that length we wanted. So we could note it as P naught P1. Good. So Pythagorean tells us that this is P naught P1 squared, that distance squared, is really equal to x sub 1 minus x sub naught squared plus y sub 1 minus y sub naught squared. Good. Or if we take the square root of both sides now, then that distance, P naught P1, is equal to the square root of the sum of these two squares. So x sub 1 minus x sub naught squared plus y sub 1 minus y sub naught squared. Good. So that's our distance formula. Okay, so let's keep this formula in our back pocket as we go back and revisit the original question of finding an approximation to a curvature. For example, suppose that a curve C is defined by the equation y equals to f of x, where f is continuous on from A to B. So here's our curvature. Let's put a grid just to get a good approximation. So let's say that there is a y-axis over here, and along here there's an x-axis, and let's say that this guy comes down to here is A, and then we come back over here and we'll call that B. Okay, so we're going to find an approximation to this curvature, and what we're going to do is we're going to break up the domain. Now, we don't want to just break it up into any random intervals. We want to break it up into n even intervals. So we're going to take the distance between B and A, so B minus A, that whole distance from here to here, and we want to break it up into n different values, and we'll call that delta x. Okay, so switching over to a different type of notation, we'll say that A is also going to be known as x sub 0, and then right next to it will be x sub 1, and then x sub 2, dot, 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 dot. Somewhere over here we'll have the x sub I minus 1. Right next to that, x sub I, and then x sub I plus 1, x sub I plus 1, and so on and so forth, all the way up until we get to the x sub n minus 1, and then B will also be known as x sub n. Okay, this is, well, maybe it's not quite that neat, but it's supposed to be done in a way where the gap between each one of these is always delta x. so that this little gap right here, this is delta x. Let me put it above it. So that this little gap right there, this is delta x. And this little gap right here, this is delta x. And this little gap right here, this is also delta x, right? So they all have the same gap between them. Okay, and then so this will lead to a point right above. This will be point naught, which is x sub naught comma y sub naught. And then the one right next to it would be this point here, which would be point 1, P1, which is x sub 1 comma y sub 1, and so on and so forth. So over here somewhere we'd end up with the x sub ith dot, the x sub I minus 1th dot, and so on and so forth. Good. And next we're going to connect those line segments. I go from, say, there to there, and so on and so forth. Okay, so your author created a nice little graph for this that looks a little neater, so let's look at that. Okay, so this is similar to what I was trying to build, only neater, nicer looking. So remember, we were trying to find the length of the curvature C. Well, that's this blue one. The blue one is known as y equals to f of x, and C is the length of that curvature, right, from an input value of A all the way out to B. Okay, so we subdivided the space underneath, so we're interested as x ranges from A to B. Let me add a couple things. So we know that A also is known as x sub naught, and that's its alter identity. And B is also known as x sub n, right? The one that comes right before it would be known as x sub n minus 1. Good. Okay, so as we go somewhere through it, somewhere in the middle we'll have the ith 1, and then right before that would be the x sub I minus 1 value. Okay, so remember that all of these are the same width, so this would be delta x there, and so would this, right? They all have delta x width, right? And so delta x is equal to b minus a divided by n. Good. So we obtained the polygonal approximation to C by dividing the interval from A to B into n subintervals with endpoints x sub naught, x sub 1, dot, 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 all the way out to x sub n, and equal widths of delta x. If y sub I equals to f of x sub I, then the point P sub I is also known as x sub I, y sub I, right? So that's just referring to this point right here. This point P sub I is also this one. X sub I, comma, y sub I. Would be this point right there, also known as P sub I. Be that point right there. And it lies on the curvature that we're interested in. Lies on C, and the polygon with vertices P0, P1, dot, 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 all the way out to Pn, right? So the sum of all the little red straight lines, right? That's the polygon. This is an open-ended polygon as opposed to a closed-ended polygon that maybe we're more familiar with. But this is an open-ended polygon, which is just a bunch of straight lines being connected, right? And they have all of these vertices. All of these points are vertices on our open-ended polygon, starting at P0 all the way out to P sub n. And we know that the sum of all those lengths, all those individual straight line segments, is going to be a pretty good approximation to the curvature C. Okay, so now if we let capital L be defined as the distance we want, it's equal to the length of the curvature C from x equals to a, to x equals to b, right? So it's exactly what we want. That's capital L, that's what we're after. Well, L then is got a pretty good approximation. Let's give it the wiggly equal signs to show that it's an approximation. It's a pretty good approximation to sum up all those lengths, all those straight lines, right? So it was the line that connects point 0 and point 1 plus the segment, the length of the segment that connects point 1, point 2, plus dot, 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 dot. We see that somewhere in the middle we'll have p sub I minus 1, p sub I, plus dot, 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 dot. And then at the end we have p sub n minus 1 out to p sub n. Okay, so that's a pretty good approximation. And we know that we can use Riemann sum notation to simplify that a little bit. So we'll say that L is approximately equal to Riemann sum as I goes from 1 to n of p sub I minus 1 to p sub I, and confirming that when I equals to 1, we get that first one right there, p sub 0, and then p1, so that'd be that line segment that connects this one, and that process moves forward, and the very last one is when I equals to n, and then this will be n minus 1, so it describes that one right there. Oops, let's make sure that that's an n. Okay, well, that's a pretty good approximation, and we can get an even better approximation, in fact, an infinitely better approximation. We can say it's equal to the limit as n goes to infinity of this Riemann sum. Good, so that's where we're heading with this. Okay, so what we've done is we've defined the length L of the curve C with the equation y equals to f of x defined between A and B as the limit of the lengths of these inscribed polygons. So capital L equals to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of these individual segments as the distance from point p sub I minus 1 to p sub I. Okay, so let's further develop this. Now let's go back to our distance formula and figure out what this is right here. Okay, so let's go back up here to this picture, and I want to focus on finding this length right there, the segment that connects p sub I and p sub I minus 1. So I'm going to focus in on this, but I'm going to zoom in on it. I'm going to cut out a little piece and zoom in on it. So we have this. Okay, so this point here, p sub I, is also known as x sub I, comma y sub I. And then this point over here, well, that's also known as x sub I minus 1, comma y sub I minus 1. Okay, and so as we saw before, the distance p sub I minus 1 to p sub I, that is going to turn out to be equal to the square root of, and then it's the difference of the x's, x sub I minus x sub I minus 1 squared plus the difference of the y's. Y sub I minus y sub I minus 1. Good. Remember earlier when we were trying to figure this out, we created a little triangle that went underneath this. And we created the triangle that connected this to this, and then another line there. And we thought about this triangle that's created. So we thought about this distance there. That would be the x sub I minus x sub I minus 1. And we thought about this distance there, which would be the y sub I minus y sub I minus 1. And then, thanks to Pythagorean, this distance squared plus this distance squared equals this distance squared. And that's the distance we're interested in. This is the distance p sub I minus 1, p sub I. Right? So this distance squared plus this distance squared. Let me put it in highlighters. The green distance squared plus the blue distance squared equals this yellow highlighted distance squared. Right? That's where that comes from. Okay, but we can simplify this a little bit more because remember that we said that we divided our space. Remember, this was sort of a larger space that went that way out to B and then came back this way out to A. And we broke up our space into n equal values. So we had that delta x was equal to b minus a all over n. And so each one of these gaps was a delta x gap. Delta x. So this is delta x. This right here is delta x. Well, likewise, we can adopt the same idea and say that this is also otherwise known as delta y sub I. So we can refer to this distance here as delta y sub I, whereas this one is delta x. Now we could label it delta x sub I to kind of match, but it's not needed here because all of them have the same width along the x-axis. Right? Along the y-axis, they don't all have the same width, so we do have to keep track of which one it is by keeping track of this little index here of I. But in this direction, the little I there is not needed simply because they're all the same width. They all have the same gap of delta x. So we can replace this with delta x squared, and we can replace that, oops, this is supposed to be a squared, and that with delta x sub I, delta y sub I squared. So p sub I minus 1, p sub I is really equal to delta x squared plus delta y sub I squared, and then all of that gets square rooted. Good. Okay, so now we can go back to our formula and replace this with that. Okay, so now we have that capital L, what we wanted, was equal to the limit as n goes to infinity of the Riemann sum as n goes from 1, I'm sorry, not n, I goes from 1, I goes from 1 to n of, and then we had this, p sub I minus 1 to p sub I, right? That's what we had before. But now we just discovered that this is really equal to this, so we can replace it by that. Make some space here. So now we have that capital L is really equal to the limit as n goes to infinity of the Riemann sum, oops, Riemann sum as I goes from 1 to n of delta x squared plus delta y sub I squared, square root of that whole thing. Okay, we're making progress. Looks a little bit better, but we still need to do some more work. We want to find a better way of expressing this, a more useful way of expressing this. So to do that, we're going to revisit the mean value theorem, if you remember. So I'm going to revisit this picture here, but there's a lot of stuff going on here. So I'm just going to look at the exact same thing before I wrote all over it. And we're going to think about the mean value theorem and how that helps us. So here, the exact same thing. We want to find this length here in this little red length here. Okay, so remember that the mean value theorem states that if we have a function f of x, remember f of x is the blue one, f of x is this one right here, the blue one, and the blue one is continuous on a closed interval, that there must be at least one point along the curvature which is equal to, such that the derivative of that point is equal to the slope of the line connecting the two endpoints. Right? So in other words, there must be at least one point, and since we have the picture, I can kind of guess sort of where it is, say somewhere around here, such that the tangent line at that point, let's make it bigger. The tangent line at this point is going to have the same slope. So let's say that this is some point x sub I star, some little star value there, such that there must be at least one point such that f prime evaluated f prime evaluated x sub I star is going to be equal to the same slope of the two endpoints. Now, what were the endpoints? That would be this point here, which is x sub I comma y sub I, and this point here, which is x sub I minus 1 comma y sub I minus 1. Good. So the slope of the line that connects them, so that would be the y sub I minus y sub I minus 1 all over x sub I minus x sub I minus 1. Right? So this represents the slope of the line segment that connects point p sub I and p sub I minus 1. Slope of line segment connecting p sub I and p sub I minus 1, right? It's the slope. That's what this formula is. And this is saying that there must be at least one point somewhere between x sub I minus 1 and x sub I such that the derivative equals to that same slope. Okay, so that's the mean value theorem. Mean value theorem. And this is true as long as f is continuous on the closed interval between these 2 points, which we clearly see that it is here. Good. And then another way of presenting this is to multiply both sides by this denominator and saying, the most common way of saying this is that y sub I minus y sub I minus 1 is equal to f of x sub I star times x sub I minus x sub I minus 1. Good. Okay, so now this, well, it's exactly equal to this width, which we've already established as delta x. And the distance, this gap here, this distance here is going to be equal to delta y sub I, and this is delta x. So we can rewrite it as delta y sub I is equal to f of x sub I star times delta x. Good. And so now that's the formula we're going to bring up and help simplify our equation. Okay, so remember delta y would be over here, just to kind of picture it here. Let me erase this here. This curvature blue is the f of x function. Remember that there's over here some sort of a y-axis, and so this translates into y sub I minus 1, and then over here translates into y sub I, and the gap here, let's put it in red, this gap right here, this one, is the change in y sub I. So this, let's put it in green, this is delta y sub I. Okay, so we need to keep track of this little sub I because it'll change as the curvature changes. Those little gaps change. But the gaps in the x-axis direction are always delta x, so we don't have to keep track of the delta x sub I. They're always identical. Okay, good. So we're going to take this little formula back up to our equation for L. And now we can replace it right in here. Okay, so I'm going to say that now we can say that capital L is really equal to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of, and then we have delta x squared plus, and now this is what we replace. Delta y sub I is now equal to this. Oops, this is prime. Oops. This is prime from here. Oops. Derivative. This is the derivative of it. So this is going to be f prime of x sub I, f prime of x sub I star times delta x parentheses squared. All of that is inside that square root. Good. So we can square the f prime. We can square the delta x. We can factor out the delta x. And so we end up with L is equal to the limit as n goes to infinity of Riemann sum as I goes from 1 to n of delta x times 1 plus f prime of x sub I star squared. And actually I'm going to flip these around and say that L equals to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of, and I'm just going to put these in parentheses just to make it clear that the delta x is no longer inside the root. So it becomes 1 plus f prime of x sub I star squared, so the whole thing squared, and then there's this delta x. Okay, and so now this is exactly the definition of an integral. So L is now equal to the integral from a to b of this guy, 1 plus f prime of x squared, take the square root of that whole thing, dx. Good. And so we've arrived at our formula, finally. To find the length of a curvature along a function f, this is the formula that we're going to use. Okay, let's look at the formal presentation from our author. Okay, so here is the formal presentation offered to you by your author. The arc length formula. If f prime is continuous on a closed set from a to b, then the length of the curve y equals to f of x, as x ranges from a to b inclusive, is what we just determined. Capital L equals to the integral from a to b of the square root of 1 plus the first derivative of x squared dx. So likewise, we can use the notation, we can use the function notation f prime x, but that is the first derivative, and we know that that also can be expressed this way. So either way is fine. One looks, I guess this looks a little neater, I think, but it's up to you. So both mean the exact same thing. Okay, let's use it in an actual example. Let's pick something from the book. Okay, find the exact length of the curve. How about we try number 10? Okay, so finding the length of the curve as x ranges from 2 to 3, inclusive of the endpoints, and y is greater than or equal to 0. Okay, from our formula, we know we're going to need the derivative. So let's solve for y. This is 3xy squared equals to x squared minus 4 cubed. So dividing both sides by 36, we get y squared equals to 1 over 36, x squared minus 4 cubed. And then we take the square root of both sides. So y equals to 1 over 6 x squared minus 4 raised to the power of 3 over 2. We ignore the plus or minus, of course, because we're told y is definitely positive. Okay, so now we can take the derivative. So let's do dy dx on the y function. So let's take d dx on the other side. This is x cubed minus 4. There's a 1 over 6 there, to the power of 3 over 2. So dy dx is equal to 1/6 times 3 over 2, x squared minus 4 to the power of 3 over 2 minus 1 times the derivative of the inside part, thanks to our chain rule, x squared minus 4. So this will simplify to dy dx is equal to, let's see, these guys reduce. This goes into there twice. We end up with 1/4 x squared minus 4 raised to the power of, and then if we rewrite this as a 2 over 2, we'll end up with a 1/2, the 1/2 power, times, and then the derivative of this is just going to be an extra 2x. So again, the 2 and the 4 will reduce, 2. And so I end up with, let me put it up here, statement of dy dx is then equal to 1/2 1/2 x, and then x squared minus 4 to the power of 1/2. Okay, so now our formula was the integral, so capital L is going to be equal to the integral as x ranges from 2 to x goes to 3, from 2 to 3, on, and it's going to be 1 plus dy dx, that's this guy, here I'll write it down, dy dx squared, and then it's the square root of all that, dx, right? That's our formula. So capital L is going to be the integral from 2 to 3 of 1 plus, and now right here we replace it with 1/2 x, and then x squared minus 4 to the 1/2 power, and then all of that gets squared, and then all of that gets square rooted dx. Okay, further simplifying this. Okay, further simplifying this, this is equal to the integral from 2 to 3 of 1 plus, and now we square these guys, so we'll end up with 1/4 x squared, And now this is raised to the power of 1/2 being squared. This is going to cancel out, and we end up with x squared minus 4. And then all of that is inside this giant root dx. Good. So now I'm going to distribute, and we end up with capital L equals to the integral from 2 to 3. And this is 1 plus 1/4 x to the 4th power minus minus 1, so that would be x squared minus x squared. Square root of the whole thing, dx. So let's pull this up here. Capital L equals the integral from 2 to 3. I'm going to move these around and do a clever subtraction. So let's factor out a 1/4. 1/4 parentheses x to the 4th power minus 4x squared plus 4. And all of that is inside this square root dx, right? So just to make sure, just to check, if I distribute, I get 1/4 x to the 4th. If I distribute there, I get the minus x squared. And if I distribute there, I get a plus 1, which is that guy right there. Okay, so factored out that 1/4. And now this is like a quadratic in disguise. Think of, say, u to the power of 2 squared minus 4u squared plus 4, right? So if it was blank squared minus 4 times blank, if I just had a say like a w squared minus 4w plus 4, then this factors out nicely as w minus 2 squared. Good. W minus 2 squared. Okay, so this is kind of like a quadratic in disguise here, where instead we want to treat these as x squares. Okay, so all of that means that it simplifies to be L equals the integral from 2 to 3. Now the square root of 1/4 is just going to be 1/2. And then we'll end up with x squared minus 2 squared, square root of that, dx. Good. And then the square root and that squared simplify to give me L equals the integral from 2 to 3 of 1/2. And then that's just going to be x squared minus 2 dx. Okay, well that's really easy to integrate. So that will mean that L equals to 1/2 on the outside, and then that's going to be 1/3 x to the 3rd power minus 2x evaluated as x ranges from 2 to 3. So L equals to 1/2 1/3 blank cubed minus 2 times blank minus, and then again in parentheses, 1/3 blank cubed minus 2 times blank, parentheses, parentheses. So here we put 3 and put a 3 there, and here we'll put a 2 and a 2 there. So all we have to do is simplify that. That's going to be L equals to 1/2, and then this just becomes 3 to the power of 2 minus 6 minus, and that's going to become 8 over 3 minus, and then plus 4, plus 4. Okay, this is going to become 9 minus 6, which is equal to 3. And then 3 plus 4 is going to be 7. So this is going to be L equals to 1/2. 7 minus 8 thirds. 3 plus 4 gives you that 7 minus 8 thirds. I need a common denominator of 3. So let's put a little 1 there. Multiply this by 3 over 3. We get 21 thirds. It's getting kind of messy, so I'm just going to go over here. So L equals to 1/2 times 21 thirds minus 8 thirds, which becomes 13 over 3. So L equals to 1/2 times 13 over 3, which means L equals to 13 over 6 becomes our answer. Okay, so we were able to use our original equation, solve for y, take the derivative with respect to x, and then we can plug it into our formula. So the formula is actually not that bad once we derive it. Hopefully the homework problems won't be so bad. Okay, now you might be thinking, well, the first step was to solve for y so that we can take a derivative with respect to x. Sure, that's good. Also, we could have done implicit differentiation and solve for dy dx. Great, that would have been fine too. But you might be wondering, well, what if we really can't solve for y, but we can solve for x? Can we solve for x and take the derivative with respect to y so we can find dx dy? And the answer is yes. We got you covered with the next formula. So if a curve has an equation x equals to g of y, for y between c and d inclusive, and g prime of y is continuous, then by interchanging the roles of x and y in the previous formula, we obtain the following formula for its length. So the length of the curvature is equal to the integral from c to d of the square root of 1 plus g prime of y squared dy. Good. Or, likewise, instead of using this notation, g prime y, we can use the notation dx dy. Good. Okay, let's try one like this. Okay, find the exact length of, let's try number 13. Okay, so this statement is already, this equations are given in the form where we've already solved for x, so we don't have to worry about that part. But let's simplify this a little bit. So I'm going to rewrite this as x equals to 1/3 y to the 1/2 power y minus 3. And then distribute that, we get x equals to 1/3 y to the 1/2 plus 1. Y to the first minus 1/3 times 3y to the 1/2 power. So x equals to 1/3 y to the 1/2 plus 1. We need a common denominator. Add these two exponents, so we end up with 1/2 plus 1, which is 2 over 2. That's going to get us to the power of 3 over 2 minus, and now these guys are going to cancel out. So we get y to the power of 1/2. So we get x equals to 1/3 y to the power of 3 over 2 minus y to the 1/2 power. Good. Now we can take a derivative with respect to y. So d dy on the left-hand side equals to d dy of 1/3 y to the 3 over 2 minus y to the power of 1/2. So dx dy equals to this derivative, which will be 1/3 times 3 over 2 y to the 3 over 2 minus 1 minus 1/2 y to the 1/2 minus 1. These guys reduce, and so we get that dx dy equals to 1/2 y to the power of 1/2. Again, we can convert this into a 2 over 2, and so 3 minus 2 is 1 over 2, 1/2, and now we get minus, same thing over here, we can put a little 2 over 2, and so we get a minus 1/2. So this becomes minus 1/2 y to the minus 1/2. Okay, so that's about as simple as that gets. Now remember, our formula involves the square root of 1 plus, and it'll be dx dy squared. So let's try and do that and simplify it. So this is going to be equal to 1 plus, and now this squared will become 1/2 y to the 1/2 power minus 1/2 y to the minus 1/2 power squared, which gets me to 1 plus 1/2 y to the 1/2 power squared minus 2 times 1/2 times 1/2 y to the 1/2 y to the minus 1/2 plus 1/2 y to the minus 1/2 squared. That's just foiling all that out. And then a bunch of stuff will reduce here. So this one reduces with that one. I still have a 1/2. 1/2 to the power of y to the power of 1/2 times y to the power of minus 1/2. The exponents will cancel out to become 0, so that just becomes 1. So this reduces to 1 plus 1/4 y to the power of 1 minus 1/2 y to the power of 0, or just 1, plus 1/4 y to the power of minus 1. Good. So then, again, reducing, this becomes 1 plus 1/4 y minus 1/2 plus 1/4 y to the minus 1 power. 1 minus 1/2 equals to positive 1/2. So this becomes 1/4 y plus 1/2 plus 1/4 y to the minus 1. Let's try and simplify this. So this is the same thing as y over 4 plus 1/2. I'm going to put a little space there, 1/2, plus 1 over 4 positive y in the denominator. That's how we get rid of that negative there. Okay, so common denominator is going to be 4y. I need to multiply this one by 2y and 2y. And then I need to multiply this one by y over y, which results in 4y squared, oops, not 4y squared, which results in y squared plus 2y plus 1 divided by 4y. Okay, so now this then simplifies to give me a y plus 1 in the numerator squared. Foiling this out gives me the numerator, divided by 4y. And just to tuck it all under one big happy root, I'm going to say that this is the same thing as rewriting the denominator as 2y to the 1/2 power squared. That's a way of describing the 4y. and then the numerator is going to be this y plus 1 squared. And the only reason I did that is because now I can rewrite all of it under one big squared. So it'll be y plus 1 divided by 2y to the power of 1/2, and then the whole thing squared. Okay, so all of that was just a way to simplify that. So now let's go back to our formula. L equals the integral as y ranges from, remember this is y ranges from 1 to 9 on, and then it's going to be 1 plus dx dy squared, and then the square root of all that, dy. Okay, well, we already have an answer for all of this. That's what this is. So capital L equals the integral as y goes from 1 to 9 on the square root of, and then all of this, which is going to be y plus 1 all over 2 y to the 1/2 power. All of that gets squared, dy. And so now, of course, the squaring and the square rooting undo each other. And so we just have to figure out the integral of y goes from 1 to y goes to 9 of this thing, y plus 1 all over 2 y to the 1/2 power dy. Okay, so to solve that, I'm just going to separate these two into two separate fractions. Let's say that this means that L equals the integral from 1 y goes to 9 on y over 2 y to the 1/2 power dy plus, well, actually, I don't need to separate two separate things. Let's do this. Plus 1 over 2 y to the 1/2 power dy means L equals the integral as y goes from 1, y goes to 9. Okay, this becomes 1/2 y to the power of 1 minus 1/2, which becomes positive 1/2, plus 1/2, and then this becomes y to the minus 1/2 dy. So I can factor out that 1/2 and say L equals to 1/2, and then we have 1/2 y to the 1/2 plus 1. That's going to give me 3 over 2. So I'm going to have to multiply by 2/3. 2/3 times y to the power of 3 over 2 plus, and then here we're going to end up with y to the power of positive 1/2. So, well, I'll put it in here, minus 1/2 plus 1, which will give me positive 1/2. So I need to put a little 2 out there. And this is as we evaluate y ranging from 1 to 9. Y ranges from 1 to 9. And so we get L equals to 1/2, 2/3 y to the power of 3 over 2 plus 2 times y to the power of 1/2, evaluated as y goes from 1 to 9. Distributing it, we end up with L equals to 1/3 y to the 3 over 2 plus y to the positive 1/2, evaluating it from y goes from 1 to y goes to 9. Okay, so we're almost there. Okay, so now running out of room, let's put it over here. Now L then is equal to 1/3 blank to the power of 3 over 2 plus blank to the power of 1/2 minus, and then in parentheses, 1/3 blank to the power of 3 over 2 plus blank to the power of 1/2. Make sure it's clear that there's parentheses here, minus these parentheses here. Okay, so we're going to plug in a 9 for this one and a 1 for this one. And so this becomes L equals to 1/3, and then the square root of 9 is 3. 3 to the power of 3, that's going to be a 27, plus 3 minus 1/3 times 1 minus 1. And so 3 goes into 27, 3 goes into 27 9 times. So now we'll have that L is equal to 9 plus 3, 9 plus 3 minus 1 minus 1/3, which is going to be 12 minus 1 is 11. L equals to 11 minus 1/3 minus 1/3. Okay, common denominator, put a little 1 there. 3 over 3 there. That's going to be equal to 33 over 3 minus 1/3 equals to 33 over 3 minus 1/3. So we get that L equals to 32 divided by 3. That's our final answer. Okay. Okay, so now the last thing we want to think about now in this section is converting this length formula into a function where we might have a as a constant. So let's let, instead of just L, let's think about the integral from a, and let's think of this as a fixed constant. Fixed constant. And then up to b, and this is going to be movable. I'll just indicate that it moves by putting this little arrow thing. It moves, it changes. Okay, so that one is movable, it's the variable. And then we have the formula, 1 plus f prime of x squared inside this root, dx. Okay, so we're going to think of this as a function of b, right? So as an example, this might look like this. Why not, fixed constant, let's make it a 1, for example. It could change, it could be anything, but it's going to stay constant throughout one whole problem. But it could be 1, it could be 0, any fixed constant, say up to b. And then we integrate this, right? So we're going to find an answer to this. Hopefully it's something that can be integrable, squared dx. And when we find an answer to this, it'll be a function where we have b in there. So it'll be a function of b. Okay, well, people usually don't like b as our independent variable. They like x, but x is already being used here. So we fix that by just replacing those letters. So we can say that a equation could be s of x integrating from some constant a to x. Again, this is a constant. Fixed constant. That one doesn't move, but the x moves. So it's a function of x. And now this is 1 plus f prime of, and now we just need a different letter just so that there's no confusion. It's not the same x. Now, oops. Now you can use any letter you want. The author likes to use t, so let's use a t there. Personally, I don't like t because they look like plus signs, but it doesn't matter. It's a dummy variable, so it could be a t. You can also make it a u du, right? It doesn't matter. As long as these two variables match, then you have your integral, same as before. And the only thing that changes now is that we have a moving variable here with x. Okay, so here's what your author writes down for this. Okay, the arc length function. Okay, so we will find it useful to have a function that measures the arc length of a curve from a particular starting point to any other point on the curve. So let's draw a quick little picture to to have this in mind. So let's say we have some function. Here we have y going that way, x going this way, and we have some curvature doing that, whatever. So this is curve C, which is a function f of x. So thus, if the smooth curve C has an equation y equals to, okay, so it also goes by y or f of x or C. And it goes from A to B. So let's say that this point, well, let's make it from here, let's make that A to B over here. So let's say we're only focused on this portion of it, from A to B. Let S of x be the distance along C from the initial point P naught. So that would mean that this point here would be the initial point P naught. And so that would be P naught, which is A f of A, starting there. And then to some point Q. Q is going to be some value x. So let's say here is x. And then that translates to this point here. So this will be Q, point Q, which is x f of x, right? But x is going to be a moving variable, right? It's a function of x. So you choose your x value as long as you're within the domain. So as x changes, then this point on the curvature is going to change. It's going to go this way or that way. And so the result of our function will be equal to the length starting at P naught all the way up to that point Q as it changes. Of course, if x slides all the way to make it A, then it would be the integral from A to A, which is 0. And if this x scrolls all the way out here to be B, then it would be the integral from A to B. Good? Okay, so that's what we're looking at. So let's try an example. Okay, so earlier we worked with this equation, 36y squared equals 2, parentheses x squared minus 4 raised to the power of 3. And we were asked to find the length of the curvature, this curvature, as x ranges from 2 to 3. Okay, so the first thing we did is solve for y. So here is the solution for y. So this is some function. This is some function. And we found the curvature, the length of the curvature, as the input variable x ranges from 2 to 3. Okay, to do that, we needed to find the derivative of this function, and then we applied it to our formula for the length, and x ranged from 2 to 3. Good. We found all that there, and we found that the integral of that whole thing equals to this. And then once we got to this stage, then all that remained was to evaluate this as x ranges from 2 to 3, and then that led us to our final answer, which was that length was 13/6. Okay, let me graph this using Desmos to confirm what this answer means. Okay, so using Desmos, I can type in this as 1 divided by 6, parentheses, and then x to the power of 2 minus 4, parentheses, to the power of, and then the power of, and then this is 3 divided by 2. Okay, so let's change this color there to there. And this was from x ranges from 2 to 3. So here's the entire function, but we're only interested in this little segment as x goes from 2 to 3. So let's put a dot on there. Let's change this to f of x, so that I can do 0.2 comma f of 2. Put it on there. And then the 0.3 comma f of 3. Let's put them in red. Okay, so here is that function. This function here, y equals to 1/6. That's this guy right here, solve for y. And we were interested in the length of this curvature between x goes from 2 to 3, so we found this little length right there. Okay, so we found that this curvature here in blue, that's the one we're working with. That's y equals to 1/6 x squared minus 4 raised to the power of 3 divided by 2. And we found that the curvature, the length of that curvature, starting from x equals to 2 over to x equals to 3, that's this right there, that there, it's the same thing as the length of the curvature that connects these 2 points. So this length highlighted in green, we found that that length was equal to 13 divided by 6 units, or 2 1/6 units. Okay, so that's what we discovered here. Okay, but now what if we leave this as a stationary number? So leave this alone. We're going to start there, start at 2, starting at x equals to 2, fixed. But then we're going to leave this other value here as a variable. So we're going to choose some x value over here so that it maps, traces to some value that we called q a second ago, q, which is x comma f of x, if we're using this notation here as f of x. Okay, so we want some sort of an equation that will describe for us the length of this curvature as x changes, as x ranges, right? So it'll be a function of x. As x changes, this value will travel up and down this curvature, and I want an equation that automatically gives me the length of the curve starting at 2 and ending at some chosen value of x. So looking back at our formula, then the formula is going to be this. S of x equals to some integral starting at 2, going up to x, and then it's going to be this integral right here. Now, it's going to be a little confusing to just use this one because this already has the variable x. So let's change it, even though the equation has x in here. So let's change it to x hat, just so that we stick to the family of x's. But x hat is not the same as x, right? It's just a different letter, right? So let's put it in color all together. So let's say that x hat is the value here that moves up and down, and we're saying x hat is not the same thing as x, completely different letters, okay? All right, so now let's say this is x hat. X hat there, x hat there. All right, so that's the letter that's moving. That's the one that's moving. And now everything else stays the same. Using this formula, everything else stays the same. So I take its derivative. I'm going to find its derivative, plug it into here. I'm going to do this whole thing, same thing. So this is still going to become 1 plus dy dx squared, square root of that whole thing, dx. Remember, this x is different from that one. Okay, and then we're going to take the derivative of this function. That's our dy dx. We're going to plug it into here. So same as before. So s of x hat is going to be equal to all of that. And then we ended up with this statement here is equal to the integral as x goes from 2 to this top one, and the top one was this x hat. And I'm going to look to this final integral thing after we simplified everything. We ended up at this stage right here, which gives me the integral of 1/2 square root of, and then x squared minus 2. Oh, not square root of. Simplified even more than that. Just 1/2, and then x squared minus 2 dx. Good. And then we do this. So then we get s of x hat then is equal to 1/2, 1/3 x to the third power minus 2x, evaluated as x ranges from 2 to x ranges up to x hat. Okay, so now we plug it in and we get the following. So now when we evaluate it, we get s of x hat is going to be equal to 1/2, and this is going to be 1/3 blank, the power of 3, minus 2 times blank, minus one-third blank to the power of 3 minus 2 times blank. And so here, I'll put it in red, here we get a 2, and here we evaluate this at x hat. So the only real difference from before is that we had a constant value of 3 there. We had a constant value of 3 here before, but now we're saying, no, we don't have a constant value. It's actually a variable on its own. It's this variable x hat. So this is going to end up being a function on x hat. Good. So now we can just simplify it as best we can, but obviously we're not going to get to a point where we have a constant. We're going to have an equation involving the variable x hat. So this is just going to be equal to 1/6 x hat to the power of 3 minus, and then when we distribute the 1/2, we're just going to have x hat minus, and then this 1/2 applies to this term as well, so it'll be 8/3, so it'll be 1/2, and then 8/3, minus minus gives you a plus, and that's 4 times 1/2 is equal to plus 2. Good. And so this has an x hat here and an x hat there. Okay, so the half applied to all of it. So let's make sure that it's clear that that's out there. So s of x hat is equal to 1/2 bracket. That'll be, well, there's nothing we can simplify there. That'll be 1/3 x hat cubed minus 2 x hat minus, and that'll be 8/3 plus 4 inside these brackets, and we have our x hat here, x hat there, x hat there. And now to simplify this, we distribute the 1/2. So distributing that 1/2 across, we get s of x hat is going to be equal to 1/6 x hat cubed minus x hat, minus the x hat that goes there. The 1/2 times the 2 will reduce. minus, this will be 4 over 3 plus 2. And so we'll have an x hat here, an x hat there, an x hat there. Okay, common denominator is going to be a 3. Let's put a 1 there. 3 over 3 to simplify this. That makes it 6. 6 minus 4 is 2, so positive 2/3. S of x hat equals to 1/6 blank to the third minus blank plus 2/3. And that's about as simple as this can get. We're there. Okay, so this is our answer. This is our function that describes the length of the curvature for various values of x hat as x hat is some value chosen after 2, right, to the right of 2. So now, for example, we can confirm our work from before, because if this formula works out well, then it should give us this answer when we let x hat equal to 3. Right? Up here we found that when we used the value 3 for the upper boundary of our integral, we found that the answer was 13 over 6. Right? The length of this whole piece here was 13 over 6. But now if we let x hat go all the way out and equal to 3, we should get the same response. So let's check it. Right here. Let's check. We're going to let x hat equal 3. And let's confirm that we get the same answer. So when we plug in a 3, we should have 1/6 blank to the power of 3 minus blank plus 2/3. And that should be 3 there and 3 there. So S sub 3 should give me 1/6 times 27 minus 3 plus 2/3. This reduces. 3 goes into 6 twice. 3 goes into 27 9 times. So we have S sub 3 equals to 9 over 2 minus 3 plus 2/3. Let's get common denominator going. So put a little 1 there. We're going to multiply this by 3 over 3 to get a 6. Multiply this by 6 over 6. Multiply that by 2 over 2. And so S sub 3 equals to 27 minus 18 plus 4 all over 6. So S sub 3 equals to 9 plus 4 is 13 over 6. Yay, it worked out. Okay, so what this is a equation that can give you the length of a curve starting at a particular point. So for this case, we found the equation, the length of the curve. So this is S sub, So this means that S sub x hat is equal to the length of curve f of x from x equals to 2 to x equals this x hat. Okay. All right, so hopefully that should be enough to tackle your homework. Stop by my office hours if you have any questions.